We're going to do a work problem. We have a right circular tank with base radius 4 feet, height 10 feet, filled to a depth of 8 feet. And this is going to be an inverted tank. So it's going to have the point downward. The base radius, this will be 4 feet, and the height is 10 feet. It's filled only to a depth of 8 feet. So roughly here. And we want to find the work it takes to pump all the water out of the tank over the top. First thing I'm going to do is I'm going to create this right circular conical tank. So to do this, I'm going to take the region. We know that its base radius is 4, so we're 4 feet out and 10 feet up. So we're going to take this region, which is triangular. So here 0, 10, and this is 4 out, 4, 10. We're going to take this shaded region, and we're going to create the tank by rotating about the y-axis. We're going to rotate about the y-axis, so working it like this, we get our tank. So we have our right circular tank. However, in this tank, the water's only filled to a depth of 8 feet, so only up to here, let's say. So we have the depth of 8 feet. So the depth here is 0, 8. First step is we are going to subdivide from 0 to 8, because that's where the liquid is, into n subintervals. And in the region, the typical rectangle when it gets rotated gives us a disk. I'm going to draw it in larger, exaggerate it a little bit. So what we have is we've got the typical rectangle, which when rotated about the y-axis gives us a disk, which is really, this disk is really a circular cylinder. And what we need to do is we're going to have to get the volume of the disk. The formula we need is that work is force times distance, but force is density times volume. And I explained it's density times volume because density is pounds per cubic feet, and we're going to multiply by cubic feet, and that will give us pounds, which is our force. So we are going to come up with F sub I, which is the force exerted by that slice of liquid, and that is density times V sub I. So V sub I is the volume of the typical disk, and we know that volume is pi r squared h. That's the volume of a cylinder. So looking at this, we can see that the radius will be x, r will be x sub I actually, and the height of that disk will be our delta y. But we know that x sub I, we can't leave x with delta y, so we are going to have to come up with an equation of this line and then solve for x equals. So this line we know connects the point here, which was 0, 0, to the point 4, 10. Fast way of getting this equation of this line is y is the slope up 10 over 4x plus the y-intercept which we know is 0. So basically, y equals reducing its 5/2 x. So that is the equation of that line, 5/2 x. But we want x sub I. We want x. So we have to then solve for x. So now we just solve for x. So it's the equation x is 2/5 y. I can now rewrite R and H. So for V sub I, R is the x sub I, which is 2/5 y sub I. H is delta y. So volume is pi r squared h is pi 2/5 y sub I squared. H is delta y. We now have V sub I. We almost have the force. The last thing we need now is the density of water, and that's something that we memorize. And the density of water is 62.5 pounds per cubic feet. So we have that. With those two, we now have the force exerted by that slice of liquid. We now have that from this, F sub I is 62.5 pi 2/5 y sub I squared delta y. That's good. We have the force. The next thing we need is the distance. And the distance will be the distance it takes to move that slice of liquid to the top. So basically the distance from the top. To get that distance, we go back to the diagram and we can see that the distance will be from the slice to the top of the cylinder. Not the cylinder, the conical tank. That distance will be here. And that distance is 10, the height, upper minus lower. 10 minus the level where the slice of liquid is, which is y sub I. So distance becomes, d sub I becomes 10 minus y sub I. We now have what we need for the work. We're now ready to say what the work to move that typical slice of water is. So W sub I is the force times the distance. So it's 62.5 pi 2/5 y sub I squared. And I'm going to put the delta y at the end. And then the distance that we're moving that slice is 10 minus y sub I. We now have the work it takes to move that slice of liquid to the top. So our next step is we sum up the work it takes to move n slices. And that work is 62.5 pi 2/5 y sub I squared 10 minus y sub I delta y. And finally, we take the limit as n approaches infinity. And that's what's going to give us our integral. But notice, I don't always have to write the sigma from I goes from 1 to n. The minute I get w sub I know what the integral will look like. So we'll go to the next page and put up the integral. So the work it takes to empty the tank is the integral of 62.5 pi. Then instead of 2/5 y sub I squared, we say 2/5 y squared. 10 minus y. Delta y becomes dy. Now the only other thing is we have to figure out the limits of integration. But if we move back here, we can see that we only subdivide where we had liquid. And the water wasn't from 0 to 10, it was from 0 to 8. So we go back here, and the limits are from 0 to 8. That is the work required to empty the tank. And when we're finished, that will give us that answer.